This is our post reading group. So the sort of interlude we're doing right now is Canguilhem's text, The Role of Analogies and Models in Biological Discovery. So this text was first published in English translation in 1963, I believe. So that's the one we're reading. So we read about the first half of it last week. We should finish the text today, and then we'll have a week off, and after that we'll pick up with another Rie book. So what we looked at last week was, in the first half of this article, was some of these examples in the history of biology of this kind of analogical thinking that tries to understand the function of some part of an animal, some organ or whatever it is, based on an analogy with a technical device of some kind. And so he points out that many of the anatomical terms that are used to refer to different organs, bones, whatever, are like technical terms that so one of his examples is a vessel, for example, that we talk about blood vessels, but of course the term vessel would originally have referred to a human produced artifact used to carry or distribute liquids. And then there's a sort of analogy from this human artifact to the objects that are part of a living being. And there's a sort of transfer of the concept of this artifact onto the organ or system, whatever you want to call it, in an animal's body, and saying, so this thing in the animal's body is analogous in some sense to the technical object that humans produce. And then there's also sort of the reverse transfer, where parts of a technical object are often referred to using anatomical terms. So you describe some part of a machine as an arm. You talk about the teeth of a gear, claws, fingers, etc. So there's a kind of back and forth movement of the representation of these objects, either using biological terminology for machines or technical terminology for parts of animals. But he points out one of the weaknesses of this kind of thinking, or this way of approaching a living being, is that it sort of limits the grasp of this living being to what is already known about the technical object. So you say, okay, these tube-like things in this animal are like the kinds of tubes that we use to pump water or for irrigation or whatever. That might be kind of an interesting starting point. So you say they look similar. This reminds me of that. But if that's all you do, then you're not really getting much out of that comparison or that analogy. And of course, that analogy will only ever be partial. There's obviously going to be many properties of the technical object that don't apply to the component or the part of the living being. And so the analogy itself doesn't really tell you which of the properties of the technical object can be sort of transferred over to the living being. And in particular, it doesn't tell you, whether this resemblance or analogy is sort of essential to this object or just a sort of coincidence. Like, does it just coincidentally look like this technical object, or is there something about the functioning of this organ that is analogous or operates under the same principles as the technical object? So what I was thinking about this as I was trying to fall asleep last night, actually, a sort of analogy about this is that, so in English we refer to a certain type of bean as a kidney bean, and this is obviously based on the shape of this bean, which is more or less the same as the organs, the kidney organ of an animal. But if you were to sort of infer from this that kidney beans must have some sort of filtration property because they have the same shape as the kidneys, which also have this filtration property, then you would be making a very bad inference. Or if you were to try to develop a biological theory of kidney-shaped things, including both the kidney organ and kidney beans, you probably wouldn't get very far. So likewise, if you say that there are teeth in animals and there are teeth on gears, so there must be some sort of like gear function that they're both, or a tooth function that is shared by these two different kinds of teeth. You probably will not understand teeth in the animal case very well. And so what Canguilhem points to here or what he's going to get to in the later part of this article is that there's a sort of transition from this maybe first step or first attempt to understand the function of an organ in terms of this technical analogy, from this just sort of this reminds me of that. There's a transition from that mode of grasping the organ to this model-based grasp of the organ. So you're not just saying this organ reminds me of this technical device, but you're developing a theory of the functioning of the organ, which could be derived from or make use of technical principles. You might be saying that this organ functions in a similar way to how this machine functions, for example. But you're not just sort of relying on this resemblance or analogy, but you're developing a theory of how the organ functions, and of course that requires experimentation, testing, comparing to other related cases, etc. So it's much more cognitively demanding than just saying this reminds me of that. And of course, I mean, the hope is if you have a good theory and a good model in that sense, that you will, not only have this sort of resemblance, but also be able to learn many more things about how this organ functions that you would not be able to learn just by comparing it to some sort of technical device. And so maybe like one of the sort of like transition forms that he's sort of talking about here is the cybernetic models, or these hydrological machines that had been developed by Vaucanson and people like that in the 17th century. So these were basically just statues that had like tubes for pumping water through them, and then by pumping water into certain channels and not others, it would move the statue in a way that would sort of reproduce human movements. And so one of the examples that he points to, or that he refers to in the text, is a flute playing statue. So it has like I think this one might have been actually operated by air, presumably, since it was playing a flute. But anyway, it moves the fingers of the hands in a similar way to the movements of the hands of a human playing a flute. And so this kind of device was, primarily just for entertainment purposes. It was a kind of novelty to display. So these statues were set up around the court at Versailles. So it was these, aristocrats sort of admiring this complicated toy, essentially. And so there's sometimes a tendency to kind of dismiss these artifacts as just a kind of toy, not really intellectually interesting. But Canguilhem points to studies that had been done by the Académie des Sciences, where they concluded that the actual movements of the fingers in the hands of the statue reproduce the movements of a human hand when playing the flute. So it's not just that you produce a similar effect of flute sounds. It's also that you're sort of reproducing or simulating the way of producing that effect in like the way a human produces it. You're simulating that in the statue, and so by sort of simulating not just the effect but also the means of bringing about that effect, you can learn something about how that effect is brought about in the human case. So you have to actually study the movements of the fingers to be able to reproduce them accurately. But the sort of weakness, the part that isn't really addressed in this type of statue, is that it has no feedback. It doesn't sort of when you have the hydraulic system that is actuating the fingers, it doesn't sort of detect whether the finger is actually moved or not. It just pumps the air or whatever other fluid is being used to move the fingers in a certain way, and whether the desired result of moving the finger occurs or not is something that only the outside observer can detect, and then maybe has to adjust the machine to make it perform as desired. Whereas a more sophisticated machine would involve not just a sort of actuation like the hydraulic system, but also some sort of sensor that can detect, has the finger moved, and then if so, where is it moving, what speed, etc., and then control the actuation system based on the information coming from the sensor. So here you have a feedback mechanism where the results of the system is being fed back into the regulation of that system to ensure that a certain result is achieved. And the sort of stock example of like the first real feedback machine of this type is the Watt governor, which controls the power output of a steam engine. So as the steam engine speeds up, the governor allows it to release more steam, which makes it slow down. And then if it slows down, it allows it to release less steam, which makes it speed up. So this negative feedback sort of keeps the speed relatively steady, regardless of how much of a load or how much work the engine is set up to do. And so the power output varies so that the speed stays the same no matter how much work is being done. And this is sort of like the model for all sorts of homeostatic mechanisms within an animal body that, say, keeps the temperature within a certain range, regardless of the external temperature, or keeps the concentration of a certain chemical in the blood at a certain level, regardless of what food, or within a range of how much food the animal has taken in, etc. So here we have a sort of mechanism, this Watt governor being sort of transferred, the conceptual schema of this mechanism being transferred onto an animal, physiological function. But at this point, it's still just that kind of analogy, and the next step is to try to expand this into an actual model and theory of physiological function that is not just, this reminds me of that. And so I think that's what we get to in the next bit as we go along in this text. So yeah, we can pick up. I had in the notes I had, we were on page 8. I think we're at the bottom of page 8, or the bottom paragraph there now in biology. So if that's correct, Angus, could you pick up from there?
Yeah, I can read. Now, in biology, it seems more difficult than in physics to resist the temptation to confer a representational value on a model. It is perhaps not only the scientific vulgarizer who has a tendency to forget that a model is nothing more than its function. This function consists in lending its type of mechanism to a different object without imposing itself as axiomatic. But has it not sometimes happened that the analogical models of the biologist have benefited from an unconscious validation, having as its effect the reduction of the organic to its analogy, mechanical, physical, or chemical? Despite their great degree of mathematical complexity, it does not appear that cybernetic models are always safe from this accident. The magical aspect of simulation is strongly resistant to the exorcism of science. It is true that the feedback model, for example, has shown itself fruitful in the exploration and explanation of the organic functions of homeostasis and of active adaptation. One can, however, believe that the process of nervous regulation is not really represented by it. As Cofignol has noted, when one labels as feedback the parts of the nervous system for which the mechanical model of regulation serves as a model, one seems to give the impression that organic feedback is part of the same class of objects as mechanical feedback. In fact, one has created, by bringing these together, a new class of objects whose definition would be able to retain only the operational characters common to regulatory organs and mechanical regulating arrangements. In other words, the use of an object as model transforms it, inasmuch as one takes explicit cognizance of the analogies with the undetermined object for that it is a model. A model only becomes fertile by its own impoverishment. It must lose some of its own specific singularity to enter with the corresponding object into a new generalization. When some kind of machine becomes a valid model for an organic function, it is not the machine in its entirety that becomes the model, but only the pattern of its operations such that it can be expressed in mathematical terms. Here light is shed on the great difference between the model method in physics and in biology. It consists in the fact that one cannot, at the present time at least, speak of a mathematical biology in the sense in which, as we have seen, one has for a long time spoken of mathematical physics. In physics, in using a model, for example, a flow of electricity in a metal plate as analogous to a hydrodynamic phenomenon with a horizontal comportment or component, we suppose that we can use the results of measuring the phenomenon which occurs in concreto for the description and prediction of the characteristics of the undetermined phenomenon. What guarantees the validity of this transference of metric results is the correspondence established by a special mathematical study between the general laws of distinct orders of phenomena. That is what does not exist in biology. It is true that there exists an arithmetical or geometrical biology of fairly long standing, and a more recent variety of statistical biology, but we hardly find ourselves in a position to speak of an algebraic biology. Therein lies the profound logical reason for the specific role of models in biological research. They lead to the establishment of analogical correspondences solely on the level of concretely designated objects, structures, or functions. They are unable to show the identity of the general laws of the two fields of phenomena which are brought together. It will doubtless remain so long as mathematics and biology is allied more closely to that of an engineer's formulary than to theories like those of a Riemann or a Hamilton. Yeah, so I think Canguilhem is not outright denying the usefulness of models and analogy in biology, but he is pointing out maybe a danger in confusing the way that a model is used in biology for the way that phenomena occurring in different domains that can be mathematically formalized the same way can be used to understand one another in physics. So the example that he gives of the electrical flow in the metal plate used to understand hydrodynamic phenomena or the other way around, depending on how well developed the science is with respect to one domain or another. Ultimately, I think what those two distinct phenomena will have in common is just the mathematical formalization. And there won't be any confusion as to whether, the hydrodynamic phenomenon is really the electrical flow or vice versa. But because biology has not been mathematized to the same degree, there is, far more clarity in the model than in the target systems, and greater risk of confusing one for sort of what is really going on in the other. So the mechanical model for the biological system.
I may have misheard the reading, but when Canguilhem, whatever the person, how should I abbreviate his Kang? I'll just say Kang. Kang. That sounds. How should I abbreviate his name? I don't know how to. I can't fucking say his name. Um. Do you know, like Kangle? I don't
You could
know.
just call him C, I guess, if you if you
See.
don't want to. Yeah.
Like, yeah, like, see, see, I think, if correct me if I'm wrong, but I think when I heard you reading C doesn't take the model as necessarily as like, the mathematical models even as like necessarily like, just, objective givens either. And this, they're still kind of, analogical in a certain way, but they're more but once they're but once but they but we're able to like take the analogy and eventually formalize it into a mathematic that then can be put back onto the world or whatever. So it's not like that's not like an analogy. It's that the analogy can be eventually made into a mathematical mathematical like structure which I find interesting because if I'm understanding, if maybe I misheard, because I've seen there's where we come up with a certain we observe a certain like objective pro so votively. Kang and Kodos. I see. I get it. There you see observe certain and like we manifest or see like physically construct or see a certain objective structure uh in the world or whatever. Then we as of time can adapt that structure into like a mathematical system of signs and then reinterpret the world through that system consistently. And it's sort of like maybe this is like a stretch of a comparison, like a way of like the world is sort of disclosed in a certain way, and maybe biology doesn't mind the biological analogies because they don't have this process of back and forth disclosure, I'd say almost, or um where like they're maybe because I don't know quite a good maybe I'm not quite I'm kind of gesturing at a weird point, but I'm almost saying like this motion where like we find or make some object, um we formal or eventually we can mathematically formalize it, and then we put that formula on the world, and then that formula makes more object, and it's almost like this pulsating motion with like mathematical models, but there isn't like that sort of pattern of like a world feeding back into itself with like the analogy. It's more like side by side, maybe. I don't know if that makes any sense at all. And this probably sounds like rambling, but
Yeah, so I think the difference between the case of physics and the case of biology that he's sort of pointing to here, so maybe it has to do in part with to some extent it's a question of degree, just of degree of abstraction. So he points out that when you sort of apply the same like physical theory to different subjects, it's not the case that it's not the case that you have sort of identified, or that you're sort of recognizing a pre-existing category of entities that all so you say that like the flow of electricity and the hydrodynamic flow are modeled, or you use the same mathematical theory to understand each of these systems. It's not the case that there's like a pre-existing category of like sort of, I don't know, abstract flow entities, and then electricity and hydrodynamics are like two sort of subcategories of that existing category. What you're doing is instead sort of creating a new category, this sort of abstract flow category that that allows you to sort of pass from one to the other. So it's only sort of retrospectively that you can say, what we were doing when we were studying the flow of electricity was sort of grasping the same kind of thing as what we were doing when we were studying the flow of water. But so this sort of higher category that includes both the flow of water and the flow of electricity only comes into existence when you use the same mathematical theory, when you introduce that mathematical theory that applies to both. But in the case of biology, it's generally not the case that you are going to so in general there are very few sort of mathematical theories in biology that you can use in that way. So he mentions genetics. So there's like population genetics is a sort of mathematical discipline. So you can it has connections with game theory actually. You can show that, for example, a certain evolutionary strategy is going to either die out in a population over time or come to dominate that population, or you can show that, say, like a certain collection of evolutionary strategies will eventually stabilize at a certain distribution in the population. So here an evolutionary strategy would be something like say like producing as many offspring as possible, but with a minimal investment in each offspring versus producing a smaller number of offspring, but with more investment in each of the offspring. So these are sort of two different ways of reproducing. And in depending on what the context is, you can show that one of these strategies is more successful than the other. This is sort of like what population genetics would do. So this is a sort of abstract theory. You don't necessarily need to know what organisms you're thinking about. You can just say any organism that has properties A, B, and C in a population of this type. Therefore the sort of stable equilibrium state of the population will be X. And then you can sort of look at real populations of organisms in the world and see to what extent that they line up with the mathematical population genetics theory. But that's a sort of exceptional case in biology. In most of biology, there's not really anything like a sort of mathematical theory you can apply. Though of course mathematics is used in biology, but he Canguilhem here sort of compares this to the role of mathematics in engineering. So of course, when you're building a bridge, you're going to calculate, the length and width and the angles of different piers, buttresses, and all these stuff. So you use mathematics, but there's no sort of abstract mathematical theory of bridges or something like that. And in the case of biology, rather than having this like sort of mathematical theory, this abstract theory that you can use to bridge one domain with another, there's more of an inclination to rely on this reduction sort of mental schema. So the idea is that like this biological phenomenon is reduced to some sort of chemical phenomenon, or we can explain it in terms of something more fundamental. And so you rely on the fact that chemistry is simpler in general than biology, that these complicated biological organisms and how they operate, we can explain this what seems puzzling by appealing to something easier to understand, which is the interactions of chemicals. So there's a kind of degree of abstraction. The difference here is partly a degree of abstraction, but also I think I guess ontological primacy, you could say, of the model in the case of biology, that we, by sort of depicting or by grasping an organism in terms of like chemical functioning, you are sort of reducing it to something more fundamental, whereas you wouldn't say that you are sort of explaining by using the same mathematical theory for electron flow and flow of water, that you have sort of reduced electrons to water or vice versa.
It's like sorry, I was gonna try to clarify my ramble earlier, but some of a friend wanted to talk to me in another server, so I'm gonna depart. Sorry about the weird ramble to begin the commentary or whatever. Probably didn't make much sense. See you, everyone.
So maybe we can go on to the next bit of the reading. Would someone else like to pick up from page 10, biological epistemology?
I can give it a shot.
Okay, yeah, thanks.
All right. Biological epistemology must, then, attach the greatest importance to the counsels of prudence that biologists address to each other inside their working community. Adrian's remark is valid not only for the type of research at which it aims. What we can learn from the machines is how our brain must differ from them. A study of Althusser has since culminated in parallel conclusions. An organism does not spontaneously fulfill any of the conditions of stability required for the correct functioning of an electric machine, in which an increase in information can never appear. In his general theory of automata, von Neumann has underlined a fact never yet disputed. The structure of natural machines, organisms, is such that failures of function do not affect general behavior. Regenerative functions, or, failing this, the supplementing of the insufficiency of one organ by another, compensate for the destruction or the breakdown of certain elements. A lesion of the organism does not necessarily abolish its plasticity. The same cannot be said of machine. I'll go on. We can, therefore, ask ourselves if the employment of electrical and electronic models in biology represents, on the level of heuristic logic, of Ars and Viente, as radical a mutation as the construction of such machines seems to be on the technological level. An analytic experimentation of the classical type, one of the conditions favoring discovery resides, we know, in the divergence between the results of prediction based on the hypothesis and the facts of observation. A good hypothesis is not always that which leads rapidly to its own confirmation, which allows at the first attempt the description of a phenomenon in an explanatory schema. It is that which obliges the researcher, by dint of an unforeseen discord between the explanation and the description, either to correct the description or to reconstruct the schema of explanation. Could not one say, similarly, that in biology, the models which have the chance of being the best are those which halt or latent tendency to identify the organic with its model? A bad model in the history of science is that which the imagination evaluates as a good one. The imagination is inclined to believe that to construct a model is to borrow a vocabulary and so obtain an identification of two objects. When the cellular boundary had been named a membrane, the laws of osmosis and the making of semi-permeable barriers seem to provide a language and a model. It seems, on the contrary, that it is in the interest of the biologist to retain the lesson of the mathematical physicist. What must be required of a model is the provision of a syntax to construct a transposable but original discourse. Before we comment on exactly what he's saying here, one thing I find kind of interesting is just the context in which this was written, where he's quoting people like von Neumann and other physicists and famous engineers, and so I wonder if at this time there was more of an attempt to merge biology and physics, if that was something people were really working toward. But I'll wait to hear.
Yeah, so maybe not so much physics, but the cybernetic sort of movement in general was very, I mean, I think there were physicists involved, but it was very interested. I mean, the whole field sort of emerges out of this idea of taking engineering concepts as a way of understanding biological phenomena. So like one example is various sort of steering type mechanisms. So like one of the early examples was anti-aircraft guns in World War II, which Norbert Wiener worked on. That so if you're trying to aim an anti-aircraft gun manually, like you have a person doing the aiming, there's often what will happen is that the delay of the movement of the gun compared to the aiming operation that the person does means that you swing too far because you move the joystick or whatever towards where you want it to go, but then there's a delay in actually making the gun move, and then by the time you stop the steering movement, the gun has gone too far, and then you swing it back the other direction, etc. So you have this sort of oscillation around the desired target rather than sort of moving smoothly towards the target. And then some of the early cybernetics work compared this to tremors of Parkinson's patients who, likewise, they might sort of move to try to pick up a cup or whatever, but the hand sort of swings around. It can't sort of move in a smooth path towards the target. And so here you have this engineering problem, this military engineering problem of how do you ensure that a human operator can aim this gun at a location without swinging past the target and then having to readjust and then likely swinging back the opposite direction, etc. This engineering problem is then sort of the techniques and ideas involved in solving this engineering problem are brought over to the Parkinson's biological problem, and obviously the hope is that you can learn from the way that the problem was solved in engineering context and then use that as a way of developing a treatment that will help Parkinson's patients. I don't know how much actual success that had at that time, because even now I think Parkinson's is not that well understood. But that's sort of like the general project of cybernetics. So yeah, there was definitely a lot of interest at the time this was written in taking sort of engineering ideas and techniques and concepts and using them to understand biological phenomena. So in this passage, he points out I think a couple important limitations to this sort of project of this sort of engineering approach to physiology. So one is what he points to, this sort of adaptability of physiological functions in the face of damage. So sometimes this is called like a graceful failure. So like if you think of a machine that, I don't know, a robot that welds a certain part of a car, for example, on the assembly line, if one of the gears of that that is involved in like the arm of the robot, for example, the gear breaks or slips out of its spot or whatever, usually that means that the whole machine is going to come to a halt, or like do something completely unexpected. Anyway, it's just sort of the functioning of the machine is sort of brought to a stop, or it's no longer useful as soon as one of these components is not operating as it should. Whereas living beings, like humans or other animals, generally are capable of adapting to injury. Obviously, depending on the degree and the type of injury. But so you can think of, for example, a person who has a stroke may lose function in one side of the body. Not be able to move their arm, their left arm, say. But over time, over months, and with rehab and so on, they sometimes are able to recover at least part of that function. So even if they maybe are not capable of like fine motor control to the same extent as they were before, they can still do things like wash the dishes or whatever. And this is something that Canguilhem sort of, I think, draws to a large extent from Kurt Goldstein, who we talked about in the Merleau-Ponty book quite a bit. So he had, I think I mentioned him last time as well. So he had worked with people who had suffered neurological damage during World War I, so brain damage or other neurological damage. And what he sort of emphasized is that these patients were not just sort of a normal person minus whatever function was damaged. Is that as someone who has some sort of neurological damage, you also sort of adapt to work around that damage and be able to engage with the world and perform the different tasks that you do in your life as best you can, despite the damage that has occurred. So the person after this injury is still a sort of whole person in the sense that they are using all the different capacities that they have to perform tasks, and they aren't just a sort of person like they were before minus one function with like a sort of gap in their functions. And so this is quite different than the way that machines function, because like I said, in the case of like the robot arm, if you remove the function of this gear that's involved in moving the arm, then you really have just sort of taken the set of functions of the machine and removed this one function, and often that results in a kind of catastrophic failure, as opposed to in the case of a human with say nerve damage in their arm, may be able to learn how to use their arm in a different way, probably not quite as well, but with some degree of success, as opposed to just a catastrophic failure. Another point that I wanted to sort of highlight in this section is when he talks about the what makes a good hypothesis is not necessarily the one that sort of directly reproduces the observations in the most accurate way. So in machine learning, there's a concept called overfitting, which is when you essentially your model that you're training from your data is more or less just memorizing the input data. It's so sort of closely aligned to the input data set that if you were to try to take that model and apply it to some other data that it hasn't seen in its training, it will get quite make very bad predictions. And so sometimes you actually want if you do your sort of machine learning training on your data set, and then you have sort of kept back a test set out of your overall collection of data, and then you find that your model has like 100% accuracy at classifying does this picture contain a dog or not in your training data. You actually would not want to use that. Like your 100% accuracy indicates that you are probably that your model is probably overfitted to, the collection of pictures that you've given it. And then if you had a picture, a set of pictures that has some different properties, like a different file format, or I don't know, the lighting is different or whatever, and you try to feed that into the model, it would probably not be very successful. So yeah, you actually don't want to have like sort of perfect accuracy in this case. And so the same kind of thing applies here in this in the sense of like a scientific hypothesis, where you sort of take in some observational data and then you are coming up with a hypothesis, and then you want to make predictions and then test that on new observations. But then if your hypothesis is like perfectly fitted, has 100% accuracy in predicting these new results, that might actually not be a good thing if you say were to try to extend, if we take our try to extend this hypothesis to a different system, a similar but not quite the same system. The hypothesis that was 100% accurate in the case of one organism might not be accurate at all if you try to extend it to a different organism. And so a good hypothesis is not necessarily the one that is best confirmed or that best matches the observations, but rather one that where whatever mismatches there are allows you to conduct further investigation and extend your knowledge in a productive way. And that's obviously much harder to measure. But so you want to have a certain amount of, I don't know, friction or like a gap between your hypothesis or your model or your theory and what you're observing, because you want to still be able to extend your intellectual apparatus, your cognitive apparatus, into new domains and not just like capture this one domain as accurately as possible. So this is a kind of like the learning process that happens in the machine learning system and the learning process that happens in science as a human institution. There's a certain analogy where you don't necessarily want to have the learning be too aligned with one specific domain, and you have to keep that sort of freedom of movement, or that gap between the learned theory and the object that you're trying to, or the domain of objects that you're trying to learn about. Maybe a more sort of everyday example of this kind of overfitting problem is you can think of like, in many jurisdictions around the world have these like standardized tests for elementary, high school students or whatever, and in many cases the like funding for the school board depends on the results of these tests and so on. And of course the result is that the schools dedicate all kinds of time just to preparing the students to perform well on this test, and so the student is learning, here's how you get a good mark on the test, but then if you sort of take the student who has gotten this great mark on the math test, say the high school math test, and then you give them like a different set of problems that's using some of the same concepts and ideas but not in the sort of exact format that they've learned to prepare for the test, they might not really do very well because they haven't really grasped the concepts. They've just learned how to do this specific type of problem that they're going to be tested on. And so here the student has overfitted the model that they've learned of solving this problem is overfitted to this one test context, and then it's not really generalizable to other domains that someone who really did understand these concepts well would be able to apply them to. And so this kind of like very limited teach to the test approach is sort of encouraging students to do this overfitting. And so likewise in science, we don't want to learn to the experiment, I guess you could say. You don't want to just produce a perfect prediction of the results of this experiment. You want to be able to extend and generalize to other related areas that have not been studied yet. Actually, last comment that just came to mind now is that these 2 points that I brought up in connection with this last passage are actually maybe connected to each other. So the fact that a human who has suffered a brain injury or neurological damage of some kind is capable of figuring out how to adapt to that injury and moving their arm is an indication that that the human has learned how to move their arm from infancy, not in this overfitted way. So like a robot arm controller, like the computer system that's controlling the robot arm, would normally be sort of adapted only to the arm in sort of the standard circumstances where all the parts are functioning properly. And then if some of the parts are not functioning properly, it would normally not be able to control that arm well. So the sort of the like model that the computer is using of arm functioning is overfitted to this one context where the arm is functioning as normal. Whereas the human who learns how to control their limbs from infancy learns in a more flexible and adaptable and generalizable way. So you can learn how like your capacity to move your arms also works with some degree of success. If you're underwater, for example, you can still pick up an object underwater even though the medium in which you're moving is very different than the sort of context that you've learned how to move. Though of course we're much clumsier and slower and so on underwater. Or you can if you have your legs tied together, you can still sort of figure out how to hop around or whatever. You can sort of adapt to these novel contexts that you haven't learned precisely because you've learned how to flexibly make use of your limbs rather than just having this like very sort of closely having a sort of limb control system that is very closely tied to the one context in which you learn how to control your limbs.
Yeah, that's a really interesting point. It reminds me of I think we talked about this in one of the later sessions for the Rie book, but in Masvita Chirimuta's book, The Brain Abstracted Neuroscience, and the computational analogy, basically, she argues that one of the key differences between the way that like machine vision AI works and human perception is that human beings sort of perceive in a way that kind of implicitly distinguishes between essential and inessential features. An example is I can recognize a cat, ordinary looking cat as a cat, but also a hairless cat. It may look strange, but I won't be confused about the fact that it is a cat because I've somehow trained on, to statistically correlate purely superficial visual features like the fur. But I can also recognize like a cat's shadow or an emoji or a cartoon cat. And yeah, there's a similar kind of flexibility in this, I guess, this grasp of something as something, or this ability to, in the case of recognizing, perceiving something as something, there are strong parallels, I think, with phenomenology and intentionality. But in the examples you were giving, with somebody adapting to nerve damage in their arm, or being able to use their hand in space or underwater, there's a similar kind of flexibility of fit, I think. Maybe Merleau-Ponty would say it's a kind of motor intentionality, but this capacity for improvisation, which isn't there in an overfitted AI system, and at least I think Chirimuta would argue in kind of artificial intelligence systems in general.
Yeah, I think it's an interesting analogy, and also because when you think of intentionality, it has to do with being directed towards an object, and part of and this is a sort of a classic Husserl concept where he talks about looking at a table or something like that. You can only perceive the table as such if you sort of recognize that that you see the table through a sort of perspective on the table. So like the sort of oblong parallelogram shape that you see that is sort of projected onto your retina is the means by which you are seeing the rectangular table. And so you have to be able to sort of implicitly grasp the fact that the table itself is the same, when seen from different angles, for example, and you only ever see it from one angle. And likewise, and so like this implies a certain like flexibility, like of being able to grasp, to extend the fact that you've seen the table from one angle to sort of a grasp of what the table would look like when seen from a different angle. And so there's obviously a very sort of low level kind of adaptation, but like many capacities that humans have for perceiving and navigating the world and manipulating objects and so on involve some capacity to extend our sort of grasp of that object from one presentation to another, where you can like see a shape and sort of understand what it would feel like to touch that shape. And so this sort of capacity to flexibly adapt to different modes of presentation of an object is part of what is required to be able to actually have a directedness towards that object as such. Like if you could only ever recognize a table by seeing it from one particular angle, then we would say that this person or this system that is only able to have this like table recognition when the table is viewed from one angle is not really like capable of grasping the table as a spatial object, for example. So I think that there's a connection between this sort of capacity for flexible adaptation and extension to different circumstances and directedness towards an object as such, as opposed to just a mode of presentation of the object.
Yeah, sorry to linger on this point, but that reminds me also of the sort of levels of I guess virtual perception that Merleau-Ponty describes in Structure of Behavior. The syncretic, yeah, that's true. We do a lot of lingering. The syncretic, I don't remember the names of the other ones. Syncretic something and symbolic. But the example of the syncretic that he gives is the toad that is unable to unable to prevent itself from trying to eat the worm that is behind glass, even though it's constantly frustrated in its attempt to eat the worm. And yeah, maybe there's something. I think there's a sense in which the toad, there's a kind of proto-objectivity of the worm for the toad, but obviously very little capacity to improvise with respect to the need to kind of immediately discharge this instinctual response. But yeah, maybe there's something I don't know, something like gradations of improvisation in, I guess, the noema with more and more complex forms of life. So that you have the chickens that can learn the lighter than relation, and then at the highest end, the human musician who can improvise on an instrument that they haven't played before.
Yeah, that's I think a great way of tying this reading back in with the Merleau-Ponty reading we did a few months ago. I always feel bad for the toad who is just trying to get breakfast and then keeps failing for some incomprehensible reason. Okay, so we can go on to the next bit. I think maybe I can read this one. Okay. By saying that the extension of the model method does not perhaps constitute a revolution in the biological heuristic, we wish simply to say that the criteria of validity of research by models remain in conformity with the schema of the dialectic relationship between the experiment and its interpretation. What validates a theory is the possibility of extrapolation and prediction, which it permits in directions which the experiment, keeping to its own level, would not have indicated. Similarly, models are judged and tested one against another by the completeness of the accounts they give of the properties to which they direct attention in the object of study, and also by their aptitude for revealing properties hitherto unnoticed. The model, one could say, predicts, but mathematical theories in physics do so also. We will not contest Gray Walter's view of the importance of the results obtained in the study of the superior functions of the brain and of learning by the construction of functional models which do not claim to imitate elementary structures. Yet despite a discreet humor at the mutual expense of the patterns of experimentation recommended by Claude Bernard, Gray Walter, when he fixes the rules of a legitimate usage of models, rediscovers, scarcely altered, the classical criteria for the criticism of experiments. It is legitimate to study the model of an undetermined process if three conditions are fulfilled. Some characteristics of the phenomenon must be known. The underdeterminism cannot be total. To reproduce what is known of the phenomenon, the model must include only the strictly necessary operating elements. The model must reproduce more than the initial amount known, whether this enrichment of knowledge be foreseen or not. To illustrate these rules, the chosen example is that of the models of the nerve. It is an excellent example which enables us to follow the successive identification of the nerve with a non-isolated passive electric conductor, submarine cable, then with an electrochemical assembly, Lilly's artificial nerve, 1920 to 1922, simulating the propagation of an impulse and the establishment of an insensitive period, and finally with a model of an electric circuit combining a battery with a grid leak condenser, capable of exhibiting the equivalent of 18 properties of nerves and synapses. One sees by this example that the succession of models for the same object of research obeys the norm of dialectical substitution of theories, with the obligation for a new theory to account at once for all the facts which the antecedent theory explained, and for those which could not be brought within its jurisdiction. As for the material technically put to work in the model itself, it is for its role that it is chosen, at a given moment, and not for its intrinsic nature. The electrical model of the nerve, says Grey-Walter, does not prove by the fact of its greater efficiency that the activity of the nerve is electrical in nature. From the point of view of the theory, the model is nothing other than the equivalent of a series of mathematical expressions. This last affirmation seems to us to be a very important one, insofar as it allows us to see the shape of the future, rather than the details of the past. The model method will really cause a revolution in biology when, without equivocation, the biologist borrows from other sciences not so much particular sorts of model, as models which are examples of structures unaffected in themselves by the mathematical constructions which unify their phenomenal disparity. The model will no longer then be the electronic arrangement as such, but rather the common function of such and such electronic, thermodynamic, or chemical arrangements, function of rectifier, valve, etc. This supposes, as we have already said, the formation of a mathematical biology, which does not necessarily mean an analytic biology, but a biology in which non-quantitative concepts, like those of topology, for instance, permit not only the description of phenomena, but the enunciation of theories involving them. I'm going to read the next bit here too as well. To sum up, the use of models in biology has shown itself more fruitful in the study of function than in the investigation of structure and the relations of structure to function. It has been possible to study analogies of general performance between models and organs without assuming analogies between the constituent elements and between the elementary functions. When quote-unquote neural nets had been constructed as a method of mathematical approach to the properties of the neuron, one might have believed that a model of the neuronic relay had been proposed. But the neurophysiologist did not recognize in this model the relative independence of the functions of the brain with respect to the integrity of its structure. On one hand, the nerve cells are not interchangeable relays. On the other, their partial destruction does not bring about necessarily the loss of total function. So this is sort of talking about what I was presenting earlier about how the role of a theory is not necessarily just to predict experimental results that have been studied already, but also to point in the direction of new investigations. So you say, we have this model, and this, if we take this model seriously, then it should work for this other domain that hasn't been studied yet. So let's study that domain and see to what extent the model works. And if you find that it doesn't work, then maybe you have to modify your model or come up with a new one. And so, like in the case of the nervous system, the sort of series of models that were presented over the decades. So like one version is just that the nerve is just an electric cable. So this is like comparing the model here is the telegraph cables that were used underwater. So there was a transatlantic cable at some point in the 19th century, I forget exactly when. So you can send a telegraphic message from the UK to North America. And in this case, you just have the electrical signals generated at one end and just sort of passively transmitted along the cable to the other end. And it turns out that nerves do not really function in this way because the nerve, so that there are synapses. So you have one nerve cell that produces an electrical charge, or that then there's a gap between one nerve cell and the other, which results in which is only bridged by the neurotransmitters that are released from one end and received at the other end. And that so there's like not a pure sort of electrical transmission, but there's a sort of series of electrical and chemical operations that transmit. And so it's not the chemical charge is produced at each step along the way and not just sort of passively transmitted. So it's a much more complicated model of how like a signal is transmitted from the brain to, say, the legs. It involves active production of electrical charge at various stages along the whole nerve pathway from the brain to the leg, rather than one signal being produced in one place and then being passively transmitted to another place, like in the telegraph cable example. And again, he's sort of pointing to maybe like a more abstract modeling method that biology is not really ready for yet. It hasn't really gotten to this point, but he thinks that this is sort of like a direction in which it should be heading, is where you would just sort of have this abstract functioning, which would not necessarily be tied to any substrate that is involved in bringing about that functioning. And so this is sort of like the black box concept, from like engineering, for example, where if you're designing a certain type of device, you can just sort of draw a black box and say this box does this function, and you don't really have to worry about how that function is done, as long as you can, buy or build or get a device of some kind that does that function. So your overall machine can just rely on the fact that you can buy a transistor that has properties A, B, C, and you don't really need to worry about how it does that, as long as you just get something that has those properties. And so you can produce this sort of like abstract machine diagram. And so like you have like circuit diagrams, for example, where you just have like a little symbol that means there's a transistor here, there's a conductor here, etc. All these things are just sort of specified as abstract properties, and you don't have to say this specific material is being used, or the device comes from this specific company, etc., etc. So the idea is that like a real sort of revolutionary modeling approach in biology would be one that would get to that level of sort of abstraction, where you could have like a kind of mathematical theory of biological functions that could be extended in various ways to new biological circumstances. Okay, so we can go on to the last section, I think. Angus, would you like to have the honor of finishing the text for us?
Nice. Yes, absolutely. Where did it go? Okay. We are at in these conditions.
Yeah, exactly.
Okay, cool. In these conditions, we may ask ourselves if the concept of a model, of which it daily becomes more difficult to propose a definition, has not retained a few traces of the ambiguity of the initial intention in constructing it. I have indicated at the beginning of these reflections that a certain technological and pragmatic structure of human perception in the matter of organic objects showed up in the condition of man, an organism, but a maker of machines. I have only sketched out the stages by which a naive tendency to identify organisms and machines lost what this naivety may have had that was magical or puerile. But perhaps a more radical naivety, an attitude of cognizance, scientific or not, in the face of life, fundamentally inspires new attempts made to exhibit in a model such or such organic causalities. The model has for a long time simultaneously resembled the type and the scale model, the norm of representation and the change in scale of size. It seems to us today that the explanatory model and integral replica, be it concrete or logical, of the structural and functional properties of the biological object has been relegated to the rank of myth. On the side of function, the model tends to be presented as the simple imitator, which reproduces a performance, but by methods of its own. On the side of structure, it can, at the most, present itself as an analogy, never as a double. It is, then, on analogy that the model method in biology rests, whether the models be mechanical or logical ones. In all cases, the only valid analogies are to be found at the heart of a theory. Whilst waiting to promote a revolutionary heuristic tomorrow, the biological model uses today the resources of a revolutionary technology. But it would be quite unjust to forget the progress that biology made yesterday, thanks to the models of experimental analysis. To forget, for example, that scientists like Sherrington and Pavlov did not work by constructing models, And to conclude, it is ironical to remember that the discovery by Sherrington and Liddell of the myotactic reflex in 1924 furnished, in the most classical manner, a weighty argument for those who, since that time, have not been able to study an organic regulatory function without seeking to build a model of servo control. I think his point in this last paragraph is that this classical experimental approach to biology, which, unlike the cybernetic approach, doesn't try to understand the living organism in terms of a model like a complex machine with feedback processes. That this classical experimental biology, which sort of is more, I guess, purely empirical and tries to understand the organism on its own terms, discovered the myotactic reflex, which turned out to be kind of a major selling point for the cyberneticians, because it furnishes a good example of a physical feedback function, but yeah, it was not discovered by assuming that the organism was like a machine.
Yeah, so I think he's maybe giving a sort of cautionary note at the end here, saying that there may be instances where models have been helpful in biology, but there's also many cases of important discoveries that were not really done in this modeling way, where like Pavlov, for example, I think was more sort of positivist in his orientation towards biology. So it's just a matter of conducting experiments and producing a kind of predictive account of the results of these experiments. And what's actually going on in the animal to bring that about is not really, is not really the focus at that stage. And this, of course, was like the whole behaviorist, tradition in like animal psychology, where you just sort of, investigate what can you get the rats to, pull the lever and then jump on the swing and whatever to get the food or whatever. But the actual mechanisms within the rat's brain and hormonal system and all these things that bring about that learning are completely just a sort of black box again. That you just assume that the rat is a system that is capable of learning these connections between performing these movements and receiving food, and you don't really need to think about how that happens at that point. So he's sort of presenting reasons to be cautious in sort of taking the modeling approach to be sort of the definitive way of doing biology, and in particular this machine analogy, which as I mentioned was very powerful at that time, and of course still today, though maybe the types of machines that are sort of used as the analogy are not exactly the same. It's reason to be careful, but obviously not to reject the use of models in general. Okay, so I think we can end here. I can't remember if I mentioned it before we started recording or after, but so next week will be off, and then the week after that we will pick up with our reading of Ruillet's book Neo-Finalism, which is translated. In 2 weeks we will pick up with that book. Okay, so thanks everyone, and thanks for showing up. Thanks for contributions, and hope to see you in 2 weeks.